Welcome back to our Math 171 video series. In this set of videos, we'll be doing some extra practice surrounding rational functions. In our first problem, we'll find the domain of this rational function, x minus 1 over x squared minus x minus 6. We'll begin this problem by factoring the denominator, seeing as how the denominator is second power. We'll begin with the x squared minus x minus 6 and examine the minus 6. We'll try to think of two numbers that can multiply together to make minus 6. If we tried 6 and negative 1, if we multiplied those, that would make negative 6. But if we add them together, 6 minus 1 gives us 5. That's not a match. For the middle term, we want the middle term to be negative 1. Let's try some different numbers. Let's try 3 and negative 2. Multiplied together, those would give us negative 6, but added together, they give us 1. Not what we're going for. We're looking for negative 1. So, since we have only a sign error here, we'll change the signs. 3 becomes negative 3, and 2 becomes positive 2, and now we add them together. When we add, we'll get negative 1. This is a match for the middle term. This means that inside of the parentheses we're going to factor this into, we'll have x minus 3 and have x plus 2. Now we rewrite our fraction, x minus 1 on top, x minus 3 times x plus 2 on the bottom. And now, based on this new denominator, we'll set this not equal to 0 to find the domain. We'll write x minus 3 times x plus 2 not equal to 0. Let's look to the first piece. We set x minus 3 not equal to 0. If we solve this by adding 3 to both sides, we'll end up with x is not equal to 3. Do the same thing for x plus 2. We'll say x plus 2 is not equal to 0. To move the 2, we'll subtract 2 from both sides. This will give us x does not equal negative 2. We'll use these to find the domain, keeping in mind that the not equal symbol represents an open circle when we draw our number line. So now we'll draw the number line and place those open circles on it. We place an open circle at 3 and another open circle at negative 2 and place negative infinity and positive infinity on the left and right. These open circles will split the number line into 3 regions, A, B, and C, based on the positions of these open circles. Therefore, to write our domain, we'll begin with region A, which starts at negative infinity and ends at negative 2. We'll put this in parentheses to show that neither of those are included in the domain. Then we'll say union and look to region B. Region B starts at negative 2 and ends at positive 3. Again, we'll say union, and region C will go from 3 to infinity. Therefore, this is our domain for this rational function. Negative infinity to negative 2, union. Negative 2 to 3, union. 3 to infinity. If we want to find the wholes to this rational function, we'll look to the simplified form we just found. In the simplified form, we're going to look for any terms that are on the top and bottom and identical. If we look to this rational function, there are no terms on the top that also appear in the bottom. Despite the fact that x appears on top, x is attached to this negative 1, making it a binomial. The x minus 1 binomial does not appear anywhere in the denominator. Therefore, we have no identical terms. And if you have no identical terms, that means you have no wholes. We can stop right now and say that the whole does not exist, or DNE. Now we'll find the vertical asymptotes of this rational function. To find the vertical asymptotes, we'll set the entire denominator equal to 0. Therefore, we'll say x plus 2 times x minus 3 is equal to 0. If we say x plus 2 is equal to 0, and then subtract 2 from both sides, we'll end up with x equals negative 2. This will be our first vertical asymptote. Then we'll say x minus 3 is also equal to 0. If we add 3 to both sides, we'll get x equals 3. And then x equals negative 2 and x equals 3 will be our vertical asymptotes. To find the horizontal asymptotes, we must examine the powers on the numerator and the denominator. We have to consider 3 cases: if the power of the numerator is bigger, if the power of the denominator is bigger, or if the powers are the same. If the numerator's power is larger, we would say there is no horizontal asymptote, and we would say D in E. However, there is a possible diagonal asymptote if the numerator's power is bigger. Also note, it's not possible to have a diagonal and a horizontal asymptote at the same time in this class. If the numerator's a bigger power, we'll say you'll have a diagonal but not a horizontal. If your denominator is a larger power, we'll say the automatic answer will be y equals 0, will be our horizontal asymptote. However, if the top and bottom are the same power, you will divide the leading coefficients. And then we'll say y equals whatever answer you end up with when you divide. Now, if we look to our rational function here, on the numerator, we have x, which is first power. We say it's first power because it has no exponent. However, because you have an x, you can write the invisible 1 up above to remind yourself that it is first power. In the denominator, we see that we have x squared, and we'll say that's second power. Therefore, we'll say the denominator's power is larger because it's second, where the numerator is first power. This also means we can automatically say that our horizontal asymptote will be y equals 0. If you're asked about a diagonal asymptote after answering a question about a horizontal asymptote, remember, for the purposes of Math 171, you won't have a diagonal and horizontal in the same problem. So because we had a horizontal asymptote, we won't see a diagonal asymptote. Based on this, we can say that the diagonal asymptote is D in E. Also note that you will only have a diagonal asymptote if the numerator is 1 power higher than the denominator. If the numerator is more than 1 power higher than the denominator, you'll get something different called an oblique asymptote. Oblique asymptotes will have shapes other than diagonal lines. You may even see asymptotes in the shape of a parabola. It would be a little bit unusual for this course, but not completely unheard of. Here we'll find the x and y intercepts of this rational function. We'll begin with the y-intercept. To find the y-intercept, we'll set x equal to 0 and simplify the fraction. We begin by saying y equals x minus 1 over x plus 2 times x minus 3. We'll change all of the x's now to zeros. We'll cross all of them off. This will give us negative 1 on the numerator and 2 times negative 3 in the denominator. If we simplify this down and divide negative 1 over 2 times negative 3, we will get 1/6. This means that our x-intercept will have a y value of 1/6. The x value we already know because we set it equal to 0. Therefore, our y-intercept is 0, 1/6. Now to get the x-intercept, we'll set the top of this fraction equal to 0 and try to solve it. We'll say y equals x minus 1 and then set that equal to 0. So our equation is x minus 1 equals 0. We'll add 1 to both sides. When we add 1 to both sides, we'll end up with x equals 1. Therefore, for our x-intercept, we'll let x become 1, and then we already said that y was equal to 0. So therefore, our x-intercept is 1, 0. With all of the information we've collected so far, we can now try to draw a sign chart. To construct our sign chart, we'll place our vertical asymptotes and x-intercepts on a number line. We'll place the x-intercept at 1, 0. So if in the middle we have 0, we'll place a closed circle at 1. Then we'll place an open circle for each of the vertical asymptotes at -2 and 3. We'll split the number line into regions based on the asymptotes and the x-intercept. This will give us 4 regions, A, B, C, and D. We'll also write the infinities, negative infinity and positive infinity, on either side of the number line. Now to construct the sign chart, we'll plug numbers from each of the 4 regions into our equation. We'll begin with region A. In region A, we'll pick an x between negative infinity and -2. I'll choose -3 for our case here. Therefore, we'll have -3 minus 1 on top, and then -3 squared minus -3 minus 6 on the bottom. -3 minus 1 on top will give -4. On the bottom, if we take -3 squared, we will get 9. Then negative of a -3 is +3, and then -6. This will give us -4 divided by 6 if we simplify, which is a negative answer, meaning we'll have a negative region in our sign chart for region A. Now we can move on to region B. Region B is between -2 and +1. Now thankfully, we have already found that if x equals 0, y must equal 1/6. Therefore, we don't need to do any additional math for region B. Because we have a y-intercept of 0, 1/6, we know that if x equals 0, y will equal 1/6, which is a positive number. This means that region B will be positive. Now for region C, we'll pick an x between 1 and 3, and we'll try x equals 2 here. Therefore, for every x, we will put in 2, so we'll have 2 minus 1 over 2 squared minus 2 minus 6. 2 minus 1 on top gives +1. 2 squared will give 4 minus 2 minus 6. If we simplify the bottom, we'll have 1 over -4. This will give us a negative answer. This means region C will be negative, and this leaves only region D now. In region D, we must pick an x that is greater than 3, so we'll use x equals 4. On top, we'll have 4 minus 1 over 4 squared minus 4 minus 6. 4 minus 1 on top gives 3. 4 squared gives 16, minus 4 minus 6. If we simplify the bottom, 16 minus 4 minus 6 will give 6. We'll have 3 over 6, which was a positive answer. That means region D will be positive. Now we can draw our rational equations graph based on this sign chart. With our coordinate axes, we'll begin by drawing on the asymptotes first. We'll draw the horizontal asymptote at y equals 0, which is on top of the x-axis. We'll put an orange line there. We'll also draw in our vertical asymptotes at x equals -2 and x equals 3. These will be up and down lines. This takes care of our asymptotes, and we'll also mark our intercepts. Our y-intercept is at 0, 1/6, so we'll draw a closed circle on top of the y-axis but very close to 0. We'll also draw an x-intercept at 1, 0. These will both be closed circles. Now we'll begin by drawing the graph starting from the left and working our way to the right. Since region A is negative, we know that whatever we draw, it must be on the negative side of this coordinate axis. So we'll draw that down here underneath the horizontal asymptote for region A. We'll draw it forward, but then we will have to turn and go more negative once we reach this asymptote. Then we'll come in from region B, and in region B will be positive. So we're going to come in now from positive infinity. We're going to again draw left to right. We're going to allow this line to cross through those two closed circles we marked previously. And then we'll allow this line to continue decreasing, and it will run along the other asymptote here at x equals 3. Notice that at x equals 1 we crossed into region C, and in region C we must be negative. This means that once we touch this axis, we're going to have to keep going more negative. Then after this asymptote, we'll go into region D. Region D is positive, so we must come in from positive infinity. We're going to allow this function to decrease, and it will then run along this horizontal asymptote. Remember that on the left and the right side, we're not allowed to cross the horizontal asymptote, but we can cross it when we're in the middle section. So the fact that we have an x-intercept in this middle section, in between region B and C, is okay. Therefore, this will be our completed graph for this rational function.